in continuation with the digital education by Dr. APJ Abdul Kalam Technical University, here is the lecture on VLSI technology having subject code KEC 053. I am your faculty Sangeeta Mangesh from Department of Electronics and Communication Engineering, JSS Academy of Technical Education, Noida. In today's lecture, we are going to continue. This is the concluding part of photolithography process, where you are going to study different photolithography techniques, and we are going to study different performance metrics associated with the photolithographic process, the challenges and the safety concerns associated with the process. At the end of this lecture, I expect the students to understand and explain the optical, X-ray and ion beam photolithography processes or ebeam photolithography processes. That means, you should be able to explain different photolithography techniques available. Secondly, you should be able to define the performance metrics, apply them in computation of different parameters if you are asked to do so. Then you should be also able to identify or explain something known as lift off technique, which is a diversion or improved or alternative to your photolithography technique. So, this is one of the other way of doing or imprinting or transferring the pattern onto the wafer surface. So, that you are going to study in this particular thing, and you should be able to explain that. So, what are the different types of photolithography processes? There are different, as the scaling is reducing the feature size, there are difficult or there are multiple difficulties appearing, and the optical basic limitation is because of the wavelength, and therefore, optical lithography has got limitations of the wavelength and then the scattering, diffraction and other issues, and which are basically limiting the pattern transfer using optical lithography. So, you have different other techniques, alternatives also being developed, and those alternatives, three basic alternatives you are going to study. One is optical, another one is electron beam lithography, and third one is your X-ray lithography. Apart from it, variant of X-ray lithography or electron beam lithography is another one, that is known as ion beam lithography, and you have something known as nano imprint lithography also, with devices getting scale to nano scale regime, that is 10 raised to the power minus 9. Therefore, you have lot of precision involved, and the techniques of pattern transfer are altering, and therefore, you have something known as nano imprint lithography also coming up. Then you have extreme UV lithography also, wherein you are able to have the wavelength getting accommodative wavelength being used to have successful pattern transfer onto the wafer. Now, what is this optical lithography system? So, here you are having a light source. This light source is basically you are having the mask. The mask, okay, here this is called as reticle stage. Reticle stage is nothing but you have vertical alignment lines, just like on your what you call CRO, you have lines or made. Here to have the mask alignment precisely, you have these lines being made. So, that precisely your pattern transfer happens through this. Okay. So, you have a projection system or projection lens. The reticle is basically used to for the mask alignment, and this mask alignment, okay, you have the reference mask. Through this reference mask, exactly line by line the mask will be aligned, and that will be imprinted. Here also you have wafer alignment, you have always the wafer being indented, always the wafer is indented, and accordingly the wafer will be placed onto the chunk. You have a wafer stage over here, the wafer will be placed precisely and the beam will be moved, okay, and the writing or the pattern transfer will be happening, or the exposure through this particular light through the with this light source to the PR, which is okay, or photoresist coating which is available onto the wafer will be carried out. Now, because of this exposure, automatically the property of the PR will alter and your pattern will be transferred onto the wafer. So, this is what is exactly being done. Now, what are these? What are the important parameters in this case? The two important parameters are the optical properties of the optical source you are using, that is you have wavelength, and another one is the angle with which you are going to focus it, the angle with which you are going to focus it. Secondly, when you are projecting or when you are exposing it, the light beam is getting projected. So, you have some diffraction happening, as we have seen in the previous lecture, depending upon the different distance at which the mask is being placed, you have the there is one more reason due to which the diffraction happen is because of the, if there is unevenness in the PR coating also, you can have diffraction pattern. So, you need to ensure that the coating is even, therefore, you carry out the soft bake also, just to ensure that the uniform, the pinholes are covered and you have uniform coating onto the of PR onto the wafer surface. So, this is what is, you have staple table on which the wafer will be placed, you have exactly alignment using these reticles, electron beam will be focused and you will have this beam scan being done through the light source, using the light source, and the pattern will be transferred. Now, what are the, okay. So, these are the basic things which are happening. So, this is what is the system working, this is how the system is working. Now, what are the key features which are to be taken into account? I told you, first is the numerical aperture. Now, what is this numerical aperture? Is the ability of the lens to collect the diffracted light, and in optics it is the numerical aperture of an optical system is the dimensionless number that characterizes the range of angles over which the system can accept or emit light. That means, over a range within which it can produce the pattern, or which can be used, or this range, over this range you can use that beam to write onto the, or write or expose the PR, so that the pattern will be successfully transferred. And this numerical aperture is calculated as n sin theta. Now, what is this n sin theta? This is this theta, the angle over which you can, basically you are, this is the 2 theta, this is total angle with which you can project this particular, project this beam onto the wafer. So, we take half the theta, and that is basically giving you the numerical aperture. It is also that is why we this depends on the wavelength, and the dependence on the wavelength is 2 pi upon lambda, where the resolving power, it is also known as the ability to with which it is going to reproduce the, what you call, resolving power, or this particular imprint can happen, and this is given, where this is basically given by lambda upon 2 Na. So, this is what is the resolving power of, or numerical aperture is calculated. Another way to understand the same thing is over here being explained. See, you are exposing the, or you are projecting the light, and this is what is the diffracted light getting collected, and the range over which the diffracted light can produce the pattern successfully onto the wafer, that is, this is the ideal intensity, and this is the refracted getting focused onto the wafer. So, this also is calculated by 2 r0 upon d, where r0 is the radius, r0 is the radius of the lens, and d is the distance between the object from the lens. So, this is also one way of calculating it. Another way is considering the angle, you have numerical aperture calculated as n sin theta. So, these are the two techniques or two ways in which you decide the angle over which you can carry out the process of lithography effectively. Second parameter you need to consider when you are carrying out the optical lithography is the resolution. It is the smallest feature that can be printed with sufficient quality, or it is the minimum feature size that can provide, that gets that provides adequate yield for device designed to work at that size. The resolution is basically the ability to transfer the pattern effectively, accurately, and it is given by equation k into lambda divided by Na. So, this is nothing but numerical aperture, lambda is the wavelength, and k1 is the system constant which is used. Now, this system constant depends on multiple factors, you need not have to get into details of it, but this is one of the technique, or this is what is the resolution what we are concerned of. Another parameter, when you talk about performance metrics, another parameter is the depth of focus. You all know when you are focusing a camera or zooming from the camera, you adjust the lens so that the focal length gets adjusted and the precise image is formed. So, you also when you are taking a picture, all those who are handling camera know they adjust the focal length and ensure that the lens adjustment is done properly, so that the imprint or the image formation gets precisely. So, same context you have to apply over here. The depth of focus is of a feature can be defined as the range of focus that keeps the resist profile of a given feature within all specifications: line width, side wall angle, resist loss, all those features it will consider over a specified exposure range, and it is calculated by formula k lambda divided by Na square. So, k is again a system constant, lambda is the wavelength of the optical source and Na is the numerical aperture or the diffraction pattern collective which is forming the accurate precise image formation over angle over which it is being formed. Another performance metrics also over a period of time being considered, which are not of much importance to us, but just to give you an idea, those include mask error enhancement factor, and this is basically the delta CD, that is change in the resist divided by like alignment, whatever alignment in the resist or change in the whatever properties alteration ratio at which the ratio of alteration in the resist to alteration in the mask, whatever resist has altered the thing. So, this is what is basically mask error enhancement factor is being calculated. Thirdly, you have something known as modulation transfer function, and this is related to your optical what you call intensity, which is calculated as Imax minus Imin divided by Imax plus Imin. This is basically exposure tool's ability to transfer the pattern onto the wafer. So, you need not have to go about, or you need not have to, just to give you an idea, just to give you the exposure to what all things are to be taken into account or you should be concerned about. I have given you these two additional things also, but you are supposed to know resolution, depth of focus and numerical aperture. These are the main things which are to be addressed or which are to be taken into account. Apart from it, there is very important figure of merit which is known as throughput. Now, what is throughput? Throughput is nothing but the cost benefit analysis what you are carrying out, the time involved, the exposure time basically involved, and the efficiency with which the pattern is getting transferred onto the wafer, we call it as a throughput. Now, throughput is also equally important apart from these three things, that is Na, resolution and depth of focus. So, let us check out the other technique. This is known as ebeam lithography. It is, you know already, in case of my optical image or optical lithography, the limitation is the properties of the light source, that is the wavelength, and the diffraction what is being obtained. The property is also like you depends upon the type of photoresist you are using. You have positive photoresist where resins are being used, the links get or the bonds get broken, and because of that once they get exposed, the pattern gets exposed to light, that area becomes soluble in the solvent, and post what you call when you etch it into the material or develop that particular portion or that wafer, the loosened where the bonds were loosened or weakened, that portion will get dissolved automatically. Whereas, in case of negative photoresist, the cross linking in the polymer will get strengthened and those linkages will harden that area, the molecular weight will increase, that area will be hardened. Another thing you have to take care in case of my negative photoresist is you have to ensure that there is no presence of oxygen in the surrounding environment, because oxygen also hampers the cross linking of these what you call material or polymers which is available in the negative photoresist. So, negative photoresist have another problem of swelling also. I told you when they get exposed, there is a property of swelling also being seen. So, pattern transfer resolution gets affected, whereas in positive photoresist you have to ensure that you have to give proper exposure time, so that each and every bond gets weakened and proper dissolving ability gets that entire material develops that property to get dissolved. And therefore, you have, if you compare positive and negative photoresist, these are the features you need to keep in mind. So, suitably you have to make use of those photoresist, and choice of photoresist is very important when you are going for considering the throughput. So, naturally positive photoresist will have expensive thing, time consuming process, whereas negative photoresist will reduce the throughput because of the swelling and resolution. So, both are plus minus things in both the resist. So, here we are having the, to overcome that entire optical process, we are having direct writing technique where the job can be done without mask. Now, here you are using the light beam directly using the electron gun and the alignment coils. With the light beam you are directly writing onto the wafer. Now, since you are directly writing onto the wafer, you need not have to go for the mask, and the area or the where you are writing, that portion we call it as a scan field, it is called as a scan field. Now, this scan field, please remember, here you have to take care of the beam diameter. The feature size generally is 4 times the beam diameter, and the scan field is generally 2000 times we consider in when you are carrying out direct writing process. Now, with this limitation you have, please remember, you for smaller features or for multiple features you have to keep on, since the exposure has to be like PR exposure has to be precisely done, you have to scan the electron beam onto the area precisely multiple times. So, when you are turning on the beam, turning off the beam, when you are turning off you can have the back path, that is, if this particular portion you want to mark, you will start from the right side, keep on scanning, blank the beam, again come back, again scan, again come back, again scan, again come back, and this is how you will keep on writing or keep on focusing and keep on writing onto that particular area. So, slowly multiple times you have to carry out the scanning, and therefore, it is a time consuming process. Similarly, when you are scanning, the exposure may not be uniform on entire area which is being covered, especially when the mask patterns are closely spaced. So, that is known as proximity effects. So, when your masks what you call spacing is very close, or the what you call patterns which are prepared onto the mask are very closely associated, then this particular problem comes into. But the effectiveness or the resolution is very good, it is a slow process, no need of mask, your mask this one is the what you call cost is getting what you call saved, but the system is very good. There are advanced features also being incorporated, and that is known as scalpel. This scalpel is nothing but scattering with angular limitation projection electron beam lithography. So, you are able to have scattering with angular limitation projection. So, you are maintaining angular limited angular projection, and you are writing it effectively precisely onto the with the help of electron beam onto the wafer. Thirdly, you have similar technique where instead of electron beam you are using ion beam, and naturally the photoresists which are being used for this will be sensitive to the electron beam. Not in case of my optical, the photoresist which was being used was sensitive to the optical source. Here the photoresist which is being applied over here will be sensitive to the electron beam. So, naturally when the photoresist is sensitive to the electron beam, its properties will alter when it is getting exposed to the electron beam. So, this is what is the what you call electron beam writing. It is a very precise, very good thing. The problem issue or the main area which is to be targeted is you do not have uniform exposure for the entire area, especially if the areas are very small, and secondly if the patterns are very closely spaced, then also you have the proximity effects. Improving that with this projection system or this particular angular limited projection system, that is faster than the direct writing. In case of ion beam also, you are using RF ion beam and the optical projection system. So, direct ion implantation is being done, the sputtering pattern automatically will create what you will react with the photoresist, and automatically the pattern will be transferred. So, it is also faster as compared to your electron beam lithography. So, there is another figure also I am showing you. Here also you have a beam blanker, I told you the beam has to be blanked. So, there is a process or system which is blanking the beam. When beam is to be focused, it will be turned on, otherwise it will be off. For exact alignment or the focus, you have different lens systems which are ensuring that the alignment of the beam and the what you call scan field I told you is precisely getting covered, the area is properly getting covered, and the writing with the of the pattern is accurately done onto the wafer. You have the projection system also. If you are using mask, in this case if you are using mask, this system can do away without this can do without mask. Normally you are using electron beam for this one, when you are using ion beam you can use mask, but in case of electron beam you are using directly light source, then you can directly you need not have to go for the mask. But in case of ion beam you are using RF system, projecting system. So, this is basically you are using mask in that case, and projection system is being used, projected printing is being done. Then next system is your X-ray lithography, where instead of optical beam you are using X-ray beam. Now, X-ray beam has advantage of, naturally you have the advantage of wavelength, and therefore, you have better resolution here, but then there is problem with the pattern transfer, especially when you are transferring the pattern. Your source is over here and you are transferring the pattern away from the source. As you go away from the source, naturally your patterns will be there will be slight change in the pattern transfer, and therefore, you have to take utmost precaution while doing so. So, that precaution is being taken care when you are using mask. So, masks are modified accordingly, and it is ensured that the pattern transfer accurately happens. Apart from it, you are using X-ray beam. So, writing is similar to what we do in optical photolithography, but except optical beam, where you are using optical lithography, you are using UV source, here you are using X-ray source. So, you are having benefit of wavelength, which is transferring the pattern precisely. Apart from it, here there is one more thing, that is you have to use what you call arrestive coating for the X-ray light, and that is normally being used with the help of gold. So, gold plating is normally used to arrest the X-ray ions or X-ray what you call this one, and it is being controlled. So, what are the plus and minus points? We will see that also here. I will see those minus and plus points also with the this one. I will just show you this. So, you have plus and minus points, where also plus point is it is like moderately expensive, faster process as compared to your e-beam lithography, but disadvantages you have to take care of the repositioning of the mask, and another thing is X-rays are harmful. So, you have to take care of radiation is slightly harmful. So, you have to take necessary precautions when the system is being used in the what you call ambient whatever. Similarly, the photoresist what you are going to use should be of a photo sensitive material, should be sensitive to the X-rays. So, that is slightly an expensive affair, but apart from it, precision wise they are very good, and they are reproducing the output very effectively. Now, the problem areas what you need to address is, when you are transferring the pattern, there are undercutting issues with the photoresist, dimensional variations in the photoresist, the transfer pattern will not get properly reproduced, we call it resistration. then pinholes, which are small holes, can create diffraction and the pattern may have developed shadows, and because of that transfer may not happen. Dust particles, scratches and tears onto the mask, and the step coverage. That is, when you are having different, okay, you have some what you call steps or some level difference onto the wafer, that difference will not be, may not be properly covered with the photoresist, and that can land up into, like, imagine suppose you are exposing this small area. So, here your source is, it may not have proper exposure in all the direction, and therefore, the photoresist may not have exhibit the same properties when you have such kind of level differences onto the wafer surface. So, precautions you need to take care, or precautions you need to take into mind, those include, you know already the system is mechanical and electrical precautions, because system is expensive, you need to handle it precisely. The electrical sources are to be handled properly, because in case of ion beam you are using high potential, in case of optical beam you are using projection system. So, you have to ensure that those are what you call any variation free, so that precise optical source is working. As far as your X-ray beam and all the methods are concerned, the chemicals which are used in dissolving or when you are developing the particular pattern, you are using different agents, you need to handle those agents, and after use you need to carefully discard them. So, that is again environmental hazard, you have to ensure that you are taking care of that. Thirdly, when you are using X-ray beam techniques, you have to ensure that the exposure to these kind of radiations are not going to hamper the other what you call processes or other entities which are available. Not only that, many times when we are exposing or writing with the electron beam, the buried layer underneath has to be protected, or there are some if you are using high what you call source activation energy for using that particular writing pattern, that also can damage the substrate. So, you have to ensure that. So, as an engineer you also know the remedial actions. So, the remedial actions mainly are taken or are undertaken at the mask design level, and these are the things which are to be taken. Whenever you are using mask, if you are using this rectangular portion and you know the optical source is not going to create the exact pattern. So, you carry out or you try to modify the mask, so that you are creating some extra portions in the mask itself, so that when you are focusing the light, it will exactly reproduce the image. So, you are having including, similarly here also you are including. So, your pattern which was getting transferred was not proper, here also it is what is getting. So, compared to this you are having a better portion at this edge also, at this edge also, at this edge also, if you are including some. So, you are carrying out mask modifications are being done. Similarly, from the light, away from the light source, the mask dimensions will be changed of excess illumination in case of, especially in X-ray lithography, to eliminate the proximity effects or to eliminate the what you call angular effects or impact due to the angular beam getting projected onto the wafer substrate. So, adding phase information to the mask, you can add phase shift mask. Here you are using, you know already there is going to be phase shift in the light source. So, naturally you will add the same phase shift to the mask also, so that entire mask will be properly creating the replica of the pattern onto the wafer. Similarly, you can have controlled polarization of the illumination, so that you can have exact pattern transfer onto the wafer. Apart from it, you have another technique known as lift off. This lift off is alternative to your pattern writing. Now, what is being done? You are focusing, lift off. That means, instead of developing the solution, what you are doing is you are putting the photoresist, exposing it, and then layering the metallization layer onto it. Now, what happens? This photoresist is already weakened portion. It is likely to get dissolved automatically into the solvent. So, after this what you will do? So, you are sacrificing the metal layer which is coated over here, and then you will put it into the solvent and dissolve this photoresist. So, automatically this portion will get eliminated and you will have patterns getting transferred. So, especially when you have small areas to be patterned, or small trenches are to be patterned, this lift off technique comes very handy. It is alternative. We are going to see this technique again when we will study etching solutions, because it comes handy over there also. So, if you are able to answer these questions, solve the numerical which is predicting the wavelength, this and k is given and your index is refractive index is given, that is okay. If your n is refractive index, in that n sin theta is given to you. So, n is refractive index. So, if your refractive index is given, numerical aperture you can calculate, and you can calculate the wavelength of the light source from the depth of focus is being given here. You are given angle of incidence is given, you are supposed to calculate all the parameters. You should be able to apply that equation and carry out this numerical. You should be able to schematic for lift off. Basically, lift off is the technique where you are sacrificing some layer and using the PR to take out that layer, and those miniature areas or small areas are being layered, or the thin film deposition is happening in those areas. So, if you are thorough with this, we are completing or we are concluding our photolithography process, which is an important one, where you are transferring the pattern, and without pattern transfer your IC cannot be fabricated. So, let us stop over here and we will go for the wet etching or the development. So, thank you, God bless, good luck.